Great. I guess as a question, how many people use Kubernetes as a background? Great. That's great. And the talk is about why ML Kubernetes ends up on, why ML development ends up on Kubernetes, why it's kind of hard and a little bit painful, and how specifically we're trying to solve it. Um, I think a lot of people end up on Kubernetes because somebody told them that you should go there, right? So we should first figure out exactly the reasons why we got to this place. And without being too distracted, I think we figured out first the history and evolution of the AI platform, or like ML platform. You can kind of think about it first in like 2013 to 2016, where people figure out that GPUs were really good and the deep learning works, XGBoost becomes really popular, et cetera, et cetera. You kind of have these first implementations of like what a platform is. And if you think about what a software platform is, it's fundamentally something that allows you to develop without a lot of DevOps and without a lot of like things in the way, and it gives you a pathway to production. So Sybil was Google's first ML platform, and they kind of announced this. And like 2014 was kind of the start of the concept of like producing an ML platform. FB Learner Flow kind of had a kind of notebooks and pipelines flavors. FB Learner Flow was pipelines, and there's this kind of concept of like we should take things, containerize them, put them into pipelines, and that is the definition of a ML platform. And this was kind of commercialized by tools like SageMaker. SageMaker was announced in 2017. You can see a couple of years later. SageMaker includes hosted Jupyter notebooks, then the 10 most common ML algorithms, and they can tune your model to achieve the highest possible accuracy. So like we've given you a platform, right? Like you have notebooks, you have 10 algorithms, and then you have the ability to tune for the highest accuracy. And so like you kind of are given these like self-service pathways to production, but in kind of narrow ways, right? And they offer you notebooks, a pipeline orchestrator to kind of like pack your code into and schedule, and then you can serve them out of model endpoints. And these are specialized solutions like SageMaker, Vertex AI, Azure ML, whatever, Databricks, et cetera. And the question is like, what more do you need? And as like maturity increased, organizations, as probably you already know as Kubernetes users, this kind of fell apart because notebooks are not reproducible. They're like great for interactive exploration, but it's very hard to take work that was done in a dev box and kind of put it into production, or on a Jupyter notebook and put it into production. So you kind of have this like 3-stage process that was like human-centric and kind of analogizes to DevOps, not platform engineering. To get from data science to like production training, and from production training to serving, it would pass across multiple teams or multiple specialties that might be on the same team. And this process for research to production is classically like a 3-week to 3-month process, even today at a lot of organizations. And so part of the problem is like notebooks and DAGs do not scale. And then the other problem is like Airflow and Kubeflow pipelines are not really for development, right? And I think we'll touch on this a little bit later. But really what you saw in this like modern ML platform age is like moving towards something that looks like traditional software development, right? You take a main mono repo and you kind of have a feature branch, you do some development on the feature branch, and it merges back in. Your feature branch needs to be able to run an orchestrated ML experiment with artifacts and data. And then once merged back in, it goes towards this like kind of like concept of this mono repo, and then this mono repo might kick off a pipeline that does recurring training, and then maybe batch inference or online inference. And then you kind of take the results of the monitoring and logging and you feed that into a new branch, and it feels and smells very software-like at this kind of broad conceptual level, right? I don't think notebooks are strictly bad, but I think as an ML platform, your team should be moving towards a high-level process that looks like this. There's still some problems in this kind of overall structure. And so, when you look at like what teams do, this is Shopify's ML platform. What they did was that they decided that Kubernetes was going to be the fundamental base compute, and that everything they ran was going to be on a Ray cluster. If you're familiar with Ray, that's great. If you're not, you can think of it as like whatever, Spark that's a little bit more ML flavored, right? And if you're not familiar with Ray or Spark, it's just like a cluster-in-cluster distributed DSL. So basically, they architected their platform such that every user could have a Merlin workspace And regardless of the workload that they would do on it, it would be universally ray. And if you ran a ray program, it would work great. And it would reproduce in research and production because your research was done on ray clusters, your production was done on ray clusters. It was all in regular code. And this took like many years and many engineers to build, but it kind of feels great. And Kubernetes was the substrate that they chose. And if you go look at the engineering docs of like basically every single large company's ML team, like, and yours as well, because most people in this room use Kubernetes, it was all decided that that was the fundamental substrate. And we'll talk a little bit more about that in a second. But in 2022, there was kind of a scramble, and then all of the efforts to like improve ML platforms kind of went out the window. And so some teams that like used to be risk management teams for a financial services are now just calling Bedrock endpoints. A lot of data science teams feel like a little bit more front-endy because they're just calling APIs, and it's a little bit of a scramble, and like what the reference architecture for an ML platform has stopped being as clear because everyone has pivoted to building Gen AI apps, and they are all richer now than the people building infrastructure layers. So like why Kubernetes? Like everyone over the course of this like long evolution moved to Kubernetes as like the basic substrate. The first is reproducibility. Like you want to Dockerize or you want to like containerize your applications, and Kubernetes orchestrates containers. So if you want to use containers, you probably need to use Kubernetes. And you know, there's things like Cloud Run. There was a talk yesterday about like serverless, like serverless serving of LLMs with Cloud Run. Cloud Run is just Kubernetes with a markup and a limited set of compute, right? Like it's just abstract Kubernetes, and like literally even says that in their design docs. You can set up package. The setup, the package version, the driver version, and the overall environment are much more important for ML than like most other domains. And so if you don't have the right package version, Hugging Face will come and like change out the library version under you, and it just like won't run. Or if you set the different seed, no one can reproduce your beautiful results that works if your seed was 2 and not 3, right? And so like all of these things are extremely important for like reproducibility of results. Local scripts, dev boxes, run pod, Jupyter notebooks, all of these things are not reproducible and require someone else to turn them into something reproducible. And by being a declarative infrastructure for defining compute, you say, I want this compute to run on, and it produces that compute for you, right? With some asterisk on YAML being kind of complicated and annoying to manage. So Kubernetes gives you the ability to kind of reproduce your programs. And if you work on Kubernetes and you like follow Kubernetes path, your programs will reproduce, which is great because now you have also lineage, et cetera, right? Like if you have a model checkpoint, and banks do this, they have a model checkpoint and a 40-page document and a PDF. That is not reproducibility because no one can take your PDF and your model checkpoint and reproduce the same model checkpoint. It's like fundamentally cannot happen. And so like that's why we want to use containerization. Then there's scalability, right? Kubernetes lets you launch and scale replicas seamlessly and orchestrates the containers. There's demand for scaling in ML even at small organizations because it's the go faster button. There's obviously distributed training, right? Like I have a training that runs on 1 node and I want to run it on 2 nodes, and it will roughly run twice as fast because the beautiful people over at PyTorch have just developed like pretty good ways of making that efficient. Hyperparameter optimization is a basic one, right? A lot of people run HPO serially. There's not really a good reason to serially run HPO other than the fact that you cannot parallelize it because the platform that you're given cannot parallelize it. But from a cost basis, it costs you the exact same amount of time to run 8 EC2 instances for 1 hour as it does to write 1 EC2 instance for 8 hours. So if you're running HPO, like being able to scale horizontally just means you can get the task done faster and get to the next step sooner. Auto-scaling inference is important at the other side of it because with like Knative and with Kubernetes, you can scale to 0. I was talking with someone at lunch and they created something that's like this. They have 2,000 models that have unpredictable demand. You want your auto scaling to be able to scale to 0 when there's no demand, and you want to scale to infinity when there is demand for it. And you don't want to have to worry about that so much. And then because a lot of ML workloads are bursty, and this can be an offline workload, it can be an online workload, it's much more frequent that you want to like auto scale down to 0 and up to like a couple replicas sooner than your website is going to hit the traffic that requires the same level of auto scaling. Finally, data processing, like people pay Databricks an enormous markup to like run compute to do data processing. Data processing is fundamentally a very distributed exercise because data sets are big And like whether you're running Spark or Dask, et cetera, these are all just distributed frameworks. And ML requires that kind of scalability much sooner than a front end team. So like Mitchell Hashimoto will go out in the world and say that startups should not be using Kubernetes. But I think there's an asterisk on that where startup ML teams should be using Kubernetes because it's fundamentally a go faster button on specific use cases. You also get like really great like resource efficiency. So the other side of scalability is not just how big you can grow, but how efficiently you can get there. If you go to Azure and you buy one A10 GPU, which has 24 gigabytes of VRAM, they will only sell that to you with 440 gigabytes of normal memory with that. That 440 gigabytes of memory, if you're using that A10 to serve a model in production, is just entirely wasted in a VM-centric model. Unless you like take that unit of compute and like put it into a shared pool, you just cannot scale up to the like level of like a scaled ML production without like kind of slicing off the pieces and like repurposing that. Which, by the way, like 440 gigabytes of RAM and 36 CPUs, that's like perfect to like run like a Spark or a Dask job on, right? To like do data processing for a different thing. So scheduling, fair sharing, bin packing are also parts of scale so that you can both increase the number of replicas and do that efficiently. And then finally, portability, right? Stages of research, dev, and production are identical because they are happening on the same cluster or same kind of environment. You can also take your containers and launch a cluster anywhere you need to go, right? Buying H200s is hard. Buying A100s was hard for a while. And so people are chasing the ability to access compute at some fundamental level in the way that like you don't if you're serving web applications. And so the ability to kind of take your work and send it anywhere rather than being like tightly bound. The big like anti-pattern here is like whatever Databricks asset bundles are, right? It's like, what is a Databricks asset bundle? It's like some like facsimile of reproducibility and containerization, but it only runs on Databricks. And if you want to run that on like AWS or like on Crusoe, like that's just fundamentally impossible, right? And then idempotency, isolation, these are just core Kubernetes benefits as well. Finally, and this is really important, and I think it's a little bit of a point that I think ML practitioners sometimes miss, there is an ecosystem of people who use Kubernetes at most organizations. There's a guy with a big gray beard who loves Kubernetes, and you don't get why. The first three reasons are why, but the other reason is that you can connect to your existing like management, auth, observability infrastructure. Your logging, all of these come basically for free if you can plug your workflow into that. I don't know how many people like have used in the past, but if you use SageMaker, you have now fundamentally forked your entire development platform into something that's like ML flavored and something that's like regular platforms flavored. Your people at the organization know how to run Kubernetes. I was talking to someone who was like, oh, we can't serve our own fine-tuned models. That would be just too difficult to do. It's like, it's kind of too difficult as an ML engineer to be like, I can productively serve a model, but it's absolutely untrue that if you went to your platform's engineering team and said, I have a single container application that I want to horizontally auto scale. Can you run this for me with like 3 nines of uptime? Your platform engineering team would be like, sure, toss it on the pile. I have it done in like 15 minutes, right? And so like there's just like a kind of mismatch in like what people understand as like hard and easy. And part of the joy of Kubernetes is trying to get into an environment that is already easy for everybody else in the software ecosystem. Software developers don't wrestle with YAML in order to get their applications into production. Which I think like leads us to like the a side note, right? Like, does anyone use Slurm? Has anyone used Slurm? I will not touch on this. Oh, well, like Slurm is popular with researchers. You may hear about it. It's a traditional HPC framework. It's really best for research teams who press enter if no one uses Slurm and no one cares. I won't dive too deeply into it. It's a CLI-based like job submission, which like has its own fault tolerance properties. There's no online inference. And then, if you use a Slurm team, it's fine if you have a dedicated research team, like you're an AI lab, but otherwise you're like kind of splitting your resources. And then going back to that scalability point, if everything runs on one Kubernetes cluster, then you're bin packing that neatly. If you slice your world into like production and research and you have a Slurm cluster for research, those resources will definitely go offline and die and like be underutilized between like 5 p.m. and 9 a.m. the next day, right? So like you kind of, and I mean, there's workloads you can use to fill that up, but fundamentally cleaving your platform into 2 different pieces is not good for bin packing. So like, what's the catch, right? Like, why do people complain about Kubernetes if it's so much like the reference architecture that I'm describing? It happens because ML development is very different than software. There is no local development And so there's a need for GPU acceleration, distributed computes, the ability to like load large data sets, and sometimes in regulated environments, the data restrictions cannot move from the cloud into your local machine. All of these things become true fairly early on in the life cycle of an ML team. There's certainly teams that like just train tree models over a few thousand rows. Like that's not really applicable here, but most teams, like even on telemetry alone, will collect data sets that exceed what you would want to load down onto your hard disk. And so even if you're doing CPU-based, tree-based model training, like you don't want to have like a 25 gigabyte data set sitting on your local drive. Availability and efficiency matters. The compute is multi-region, multi-cloud. I was describing that it was like kind of hard to get access to compute. As a software developer, you don't need as much to think about where your compute runs, but as an ML platform, you do need to think about where your compute runs because it's not always available to GPUs. And then finally, a single project spans online and offline activities, which is somewhat atypical. You span batch data processing, research training, recurring training, inference, and there's so much heterogeneity in that process. If I'm a front-end developer, I do a front end, I build it, and I deploy it. But as an ML developer or like as an ML team, which might have different personas from like data science and research all the way through to production and cloud engineering, you actually need to take your platform and have it support a whole range of activities, right? Data processing is about like robust scheduled activities. Research training is about a high degree of interactivity. Recurring training goes back to kind of batch data processing like, but on a recurring basis, like what you want out of a workflow orchestrator. And production inference is about auto scaling and time to first token. And all these concerns need to be fit within a single platform, which was why it was so tempting by like the platforms in the box people to just separate them out into like different pieces. But fundamentally, we think that Kubernetes can support all of these. This broken fundamental assumption that software is like ML, though, leads to a process that is the core of what, when we talk to people, makes Kubernetes difficult, which is that you must develop through deployment. You can't locally run and test your code, containerize it, and then ship it off to CI. Ship it off to CI, containerize it one time, and then run it in production. You must, after every time you add a print statement or do any kind of debugging, change any method, push and pray, right? Like you push it, and then CI will go build a container. It's picked up by Kubernetes and run. 30 minutes later, you see the print statement come out, and that process is just painful. And you are being paid in the United States $100 an hour. So that is $100 of just wasted time, all right? And so like, you know, this push and pray debugging just like introduces hugely inefficient iteration loops into the process of getting your workloads running on Kubernetes, right? Like this is the problem with like you're using Cloud Run. You need to rebuild your container and you have to serve it. It's a problem with building inference applications. If you're building composite AI inference applications like a RAG system and you want to try out a different embedding model, if like trying out different models and different pre-processing and different like small changes to your application requires rebuilding your container, you're just going to iterate less frequently and build less good products. I don't know if this resonates, like you don't have to, but like if this is part of your Kubernetes workflow, I guess say something or raise your hand. I don't know if this resonates. Otherwise, you know, maybe it's a solved problem for others. Also, people like kind of loathe YAML. People don't always understand why, but I think it's like developers in the ML and data science space like to work Pythonically. If you tell them here's a YAML, Argo CD will bring up your Ray cluster, that will be a not golden workflow. And if you're like, here, just like use Python to define it, right? Like if you use Spark Connect on Databricks, like the experience is actually really good. In your Python, you go like, I would like this kind of Spark cluster, and you just like send your PySpark job to it and it runs. And then it's all magic and it's all in Python. Python is a language of choice for 95% of data science and ML developers. And the fact that like a lot of Kubernetes system forces you out of it to run kubectl, go into Kubernetes logging, and use YAMLs as the language to define your workloads, that ends up being like an anti-pattern that causes people to hate developing on Kubernetes. So like, so then I guess what makes a good ML platform, right? Like I've already analogized to Databricks a little bit. I think Snowflake is a really good example of producing a data platform. Before Snowflake, SQL worked fine if you were working on single box applications. people increasingly no longer even remember this world, but you had a server somewhere and that had a SQL server or Oracle SQL installed on it, and it had like 64 CPUs and some amount of memory. And if you wanted to run queries on data set that fit on the disk on that server and that fit within the memory constraints of that server, it was fine. Like you could write regular SQL and do it. But then your data, like this whole big data trend came out of the fact that that broke down at some point. Like you had data sets that just would not fit on a single box or could not be efficiently executed on a single box. So then for anything larger, you needed to have like OPSI infrastructure, right? You had Hadoop clusters, which 3 other people managed. And then you had to learn a different language and you had to write map reduces to like execute over it. And then there was like subsequent frameworks that tried to paper over those problems. But fundamentally, you cleaved your data warehouse into like 2 different segments. You have 2 different languages in your code base to interact with data. And that did not create an environment which was possible to have a data platform. After Snowflake, whether you're running your query for 10 rows of data or a billion rows of data, you write that identical SQL query, and so the language does not change, but it executes if on ephemeral compute that's allocated from the cloud. Your data can live anywhere, and it's all an abstraction to you where I, as the end developer, 2 weeks out of school, can write select count star from table, and it can return 10 or a billion, and the exercise of getting to that number is left as an exercise for the platform itself. And so this is magical, but this also creates the conditions that makes it possible to have a developer platform. Developer platforms enable self-service, and without this kind of magical abstraction over infrastructure, it's not possible to have like the modern data estates that you have today. So what makes great AI? What makes a great AI platform based on this kind of like motivating developer and data engineering story? One, it makes heavy computation accessible and reproducible without opinionation. The platform should not govern how you bring up compute and what the compute looks like. You should not like be restricted on the types of instances, where you run it. You should just be able to demand it and your platform will return it to you. 2, there's a standard that is shared by research and production. This is tough because research demands high velocity on this kind of heavy computation, and production needs robustness and fault tolerance and observability on the heavy computation. So it spans a wide range of concerns that doesn't exist, as we were talking about earlier, in the space of like traditional development. But finally, it makes it simple to propagate wins throughout the team. And this is like a little bit of like a strategy-ish point, right? Like a lot of ML engineers don't go like, what does it mean to propagate wins through the team? Like it starts at a basic level. Is your code modularized and importable into like different workflows, right? If your code is not modularized and it lives in notebooks that you have put on a cron scheduler, then it is not easy to propagate the wins across the team. If you have a new intern start or a new hire start, and it takes them 3 weeks or 3 months to onboard to your like Kubernetes stack and to learn how to debug everything because they didn't learn any of this in college, then it's hard to like propagate these wins into the team, right? The onboarding time is a significant consideration. So we're introducing a product that we call Kubetorch. It's not just for PyTorch, by the way. It's actually an analogy to Kubeflow. So when you think about like Kubetorch to Kubeflow versus PyTorch versus TensorFlow, PyTorch was Pythonic and had cleaner, more modular APIs. It was eager in its execution versus like Kubeflow has pipelines, Kubeflow pipelines, which is graph-like. That's the kind of joke. General service purpose, agnostic, and it plugs into a rich ecosystem. Versus Kubeflow is somewhat opinionated about the services that you had to use on Kubernetes. So Kubetorch is for infra people who love Kubernetes so that you can just plug into their world. And the data science, machine learning engineers, AI engineers, whatever the titles are going to become in 6 months, who love PyTorch and just the simplicity of Pythonic APIs. You use regular Python to define the compute and the distributed framework that you want to use, like PyTorch, TensorFlow, distributed, Ray, Spark, Dask, etc. And then for research, it takes 2 seconds to rerun locally developed code, because what we allow you to do is launch these containers as like a base, and then we'll allow you to hot sync and hot reload any further iteration into that container, so that rather than having to wait for your container to rebuild to see your print statement, you're basically suffering the time latency of just re-importing your code. on the remote. You're still developing locally. You can use any IDE you want, but it's just with your local kube config, lifting that local program to the cloud. You should still work off a team-based Docker image. And in production, you should also still use a team Docker image. The execution just happens identically because you're in your research environment, you are taking your local program, you are bringing it up on Kubernetes, and you are calling it there. And in production, if you have an Airflow pipeline or you have a fast API app to serve an inference application, you're identically calling out to the application on Kubernetes. The only difference between research and production is whether you're doing this kind of hot sync process or you are freezing it one time and you're not doing the hot syncing anymore. So I have a little bit of like a code sample, right? So like this is kind of fundamentally the API. You define this kind of compute object in code. You say kt.compute. I want one GPU, and you can say like I want this many CPUs. I want this much memory. I want it to live for this long until like inactivity TTL, right? Like I want it to live this long, and if it's idle for that long, nuke my service. And then you can define a base image, right? So here I'm using the PyTorch image in the NVIDIA container registry, but you can use your team Docker image. Then I can call distribute on it, right? I can say that I want to wire up my 4 nodes, which I want workers for, and I want to wire up PyTorch. There's only one nuance here because like there's 2 styles of launching distributed programs basically. If you're using like Ray or Spark, there's a head node or Dask, right? There's a head node and there's workers that connect to that. And if you're using a system like PyTorch distributed, like DDP, it's MPI style launching where you launch n replicas and you call into each of them, right? So in Ray, you call into the head node, and PyTorch, you call into each node. So there's just a little bit of like wiring that we need to do to make sure everything's configured. But then fundamentally, what you get back is a callable train DDP that has an identical function signature to your original train function. And you use that kind of torch-like .2 in the same way that torch lets you lift CPU workloads to the GPU, we're letting you lift local workloads kind of to the remote. And so kind of now you get back train DDP, you call that locally as you would any normal function, and you get back your iteration loop. And if you call .2 again, it's about 1 to 2 seconds to resync that code. And then at the end of the whole process, you can bake it into your team Docker image and like freeze it for good. For inference, there's a similar API. If you're familiar with tools like Modal or Base 10 or even Ray Remote, it's a little bit of a similar API. There's a bunch of orchestrators that kind of have a similar one as well. You define your compute, right? You say, I want 8 L4s to serve this DeepSeek distill. And I want between 1 and 4 replicas. You can say 0 to 4, which will auto-scale down to 0. But for a lot of inference applications, you might want 1 minimum replica, auto-scaling to 4. And so then you deploy with a CLI command, kubetorch deploy. Same guaranteed benefit, 1 to 2 seconds to redeploy your application, because we are not rebuilding the Docker image. We are using your base Docker image and then syncing any code changes on top of it. And then you can call it as normal using the from name. And now you get back a DeepSeek callable that's basically a production service. And you can do inference over this as well. I guess if the internet has been a little bit bad here, but just kind of to show you the example, you can see that if I take this regular block of code and the regular code above, you can see that like my train function is ready, it's ready, it's checking the existing service is ready, and then you can see that there's a timeout here for like 600 seconds, there's all these things, and you can see that I've actually brought up this service in just like 2 seconds, right? And this is a distributed dummy training, and that I'm able to kind of restart my training if I had made a change to the code almost instantly, right? I kicked it off at 33:48, and my losses started returning 6 seconds later, right? And fundamentally, what has happened here is that when I recall .2, the service is still alive on the remote instance, and I'm able to kind of hot reload this, such that if I were to like add a trivial change, like here, and I kill this, if I rerun this program, it should also have a 6-second iteration loop to propagate my local changes back up. And then the process is like, once I'm done testing all of this, I can actually just go ahead and like bake my PyTorch DDP function, which lives in my mono repo, into my Docker image. And then what I'll do in production is, instead of having here So you can see that the change is instantly propagated, right? Like if you're using Kubernetes and you're building a Docker container to like iterate with like Kubeflow or like Cloud Run or any other system, there's just simply no way that like your changes would propagate this quickly. And then in production, you would say like freeze equals to true. And what this will basically say is like, don't sync any more code around. Use the locally installed version of Kubetorch. Like that will freeze it. And so most of our actual users in production will have like this be a toggleable thing. You will read out an environment variable for like, is it like the development environment is prod? If it is prod from an environment variable, then we set freeze equals true. And then what you do is like you bake this whole thing into a Docker image and it will import locally out of that Docker image rather than enabling any kind of hot syncing, which is a research feature. If you want to chat or give us feedback, it would be much appreciated. We're based in New York City. We were previously working on a project called Runhouse, which was a VM-centric model of the same thing. Kubetorch is the Kubernetes-centric model. VMs are dead, and we designed our first product wrong. But we're kind of looking for feedback and people to chat with. So if anyone has any questions, happy to answer them here or shoot me an email if you're curious.